So in the beginning, mobile robots have been deployed for various applications. We can find it in industry, military, medical field, and more. To perform certain tasks, they can move around within an environment in different ways to suit the application. One of the most important applications is the gas mapping, where due to the hazardized nature of the environment, a mobile robot that equipped with a gas sensor utilized in a map to perform gas mapping. However, the issue is that the main issue that this project is addressing, that previous mobile robot missing the concept of autonomism and self-decision. So they cannot perform gas distribution map in unknown environment without human interaction. So they must be manually, remotely controlled or manually preset the settings. So we are introducing reinforcement learning in order to solve this issue. The concept of reinforcement learning is that we have an agent or the robot, and it's interact within an environment with certain actions, and it receives a reward based on that. So the objective of this project is to implement reinforcement learning for robot navigation in simulation environment, and to develop path planning method based on reinforcement learning for gas distribution mapping, and third, to evaluate the performance of path planning method that been developed. So the scope for this project can be divided in three sects. For the first section is the path planning. The path planning will be in 2D obstacles only, in the maximum size of 400 by 400 units, and we are doing for static obstacles, and we're assuming that the SLAM is ideal. So for the gas mapping, we are assuming that the gas mapping is ideal, so we are not dealing with any errors or noise from the sensors. As well, we are obtaining 2D map only, and we are not focusing on any mechanical analysis on the gas. So third is the reinforcement learning. We are using one agent or one robot, and we are using ordinary reinforcement learning, so no deep learning or neural network are involved. So the overall methodology of this project is starting by creating the environment, and as we saw the model, and we saw area, the model consists of an environment and an agent. So after we finish the model, we test it, and if it passes, then we straight away implement the reinforcement learning. We run the test, and then we analyze the output. So I start by creating a dummy model, which is only a 5 rows by 5 columns map matrix. You can see it at the left-hand side, and it consists a integer values stated in the table below, and on the right-hand side, the visualizer that receive those integer values and convert them to a color using OpenCV. So the agent or the mobile robot has attribute of motion, and to simulate this motion is very easy. We just shift the row or the columns to perform the motion, and in this model we are doing 4 degrees of freedom motion, up, down, left, and right. So however, in the real physical world, the robot should not pass through the obstacles or cross the map edges. So a collision prevent method or function is produced to prevent the robot from collision the obstacles and update the map after that. So the engine is created to test the model. It receives the map matrix, and then visualize it, and we can interact with the model with the actions. Then it receives the action, applies to the collision prevent, and if it's valid, then it's update the map and the cycle go over. So now our model is ready. We just need to implement reinforcement learning. We used to implement Q-learning algorithm for that, and Q-learning algorithm is one of the most famous reinforcement learning algorithm. It's based on 2 things. First one, Bellman equation and Markov decision process. So we just create the Q table, which consists of all the states flattened and across by the action of the robot. And by the time the robot is going and learning and utilizing from decaying from exploration to exploitation, basically the Q table is being filled up using the Bellman equation, and then eventually the robot use the the experience in the Q table to select its next action. So next, after we successfully applied the reinforcement learning on the dummy model, now we upgraded to the model that suits our objectives. So we created a 400 by 400 units map. We just created using Windows Paint, and then we apply the robot, also the gas map, and now the robot is moved in 8 directions instead of 4. So for the gas map, to create the gas map, I use the potential feed method. I'm not going to explain that further. It's not in the it's not from the objective. So, but I'm happy to listen to your question in the Q&A session. As well, the agent have an attribute of 2D SLAM simulation using Python, and also not going for these details, but also happy to have your question in the Q&A session for that. So eventually the robot sniff the gas using the olfaction simulation from the gas map, and then multiply it with the Gaussian to simulate the gas mapping. Then that was model A, and however the result was not really good, so we had to optimize it. And then we achieved model B. It's more advanced than model A. So after that, we go with model B2. It's also more advanced than model B1. In this time, we are using SLAM, 2D SLAM histogram analysis. It's helped the robot to find where to go in the hidden areas, and find the hidden areas. And for the experimental environment setup, I start by making 3 different maps with different complexity levels, and I set the robot position and the gas position as the same for each trial, and try the model A, model B1, model B3 for all the 3 maps. So this is the result for model A. We can see that it's take a really long time, and the Q values are really huge, and the result is not that much. And these are the result for model B1. The time is being reduced due to the optimization done between model A and model B1. And then this is the result for model B2. We can see that they are better than model B1 and better gas mapping. So as a summary, we can conclude that the model A is good in mapping. However, it's not good in gas mapping for map 1, and it's very bad for map 2 and map 3. And for model B1, it's achieved good in open areas like map 1 with less complexity things. However, it's not really good in the concave areas or complex areas. And model B2 is good in a complex area and hidden areas. However, it's not really good for gas mapping in the open areas as the observation of that. So in a conclusion, eventually we can say that reinforcement learning algorithm which manifested in Q learning during this study proved that it's capable of training a mobile robot to perform gas mapping in indoor areas, while the real world is much tougher and more dynamic and complex than this simulation. However, there is a bright sun at the end of the cave gate telling loudly that it's possible and promising to implement it in real world and with real mobile robot and hardware. However, we need to do some upgradings and improving. For example, we can upgrade the reinforcement learning to deep reinforcement learning in order to enhance the process and be less competition on the computer due to the Q table from the ordinary Q learning. That's all for me. Thank you.